To introduce our first speaker, Ed Corrigan, who will speak about aspects of duality, memories, collaboration.
Well, I hope you can hear me at the back, because it's like an undergraduate lecture. There's some empty seats at the front. Anyway, first of all, thank you to Nick and Adrian and Mateus for inviting me to come and talk about at least some of Peter's work, and let's see how it goes. So I want to talk about aspects of duality. Duality is an overused term. It's used in all sorts of contexts, and Peter has been involved with quite a few of them, so let's get on with it. So first of all, I'd like to mention that I've known Peter for a long time, actually. We actually overlapped as PhD students in DAMTP. He started in 1967, I think, and I started in 1969. So we overlapped. And people from that time will know that the first year PhD room, which was at the front of the old DAMT building, was also the place where preprints were assembled. And all the graduate students would meet on some occasions during the year to put preprints together. And that was probably the first occasion that I came across Peter, because our offices were in different places, and nevertheless we met very occasionally then. So you'll notice that he started before Veneziano's paper. So the ideas of duality were in the air. So the high energy behavior of a scattering amplitude in particle physics and its relationship with the low energy behavior, the resonances, was an aspect of duality that was in the air then. And then Veneziano's famous 1968 paper came out with a concrete proposal of how this actually worked. But remember, that happened during Peter's time as a PhD student, and he wasn't working on that specifically, at least that's not what I remember. He was working on other aspects of S-matrix theory and scattering amplitudes, quite a lot of the time with Alan White. And his supervisor was John Polkinghorne. And then during October to December 1971, we actually overlapped at CERN, because Peter went off to CERN after he got his PhD in 1970, I guess, or the end of 69. And he was working at CERN, but my supervisor moved to CERN. My supervisor was David Olive at that time, and he moved to CERN, and he invited me to follow him. So I met Peter at CERN, and actually Peter and Helen were extremely kind to me and to my wife, looking after us and taking us around and making sure that we didn't lack for anything. And that was really nice, actually, and it made our stay there really much more pleasant than it would otherwise have been. And then we overlapped in Durham, because as many of you will know, Peter got his first lectureship in the University of Durham, and I got my first postdoc in the University of Durham. So we were in the same department, the mathematics department, in the University of Durham, now known as Durham University, because they changed their name for some odd reason. Anyway, we overlapped there, so I'll talk a little bit about that. And then he moved to Cambridge in 1974, after I think a short stay in Princeton. And then we met after that in a variety of occasions. So I spent some time in Paris, and he came to visit us. He spent some time in CERN, we came to visit him. I went to Caltech, he came to visit me there, and so on. So in many places we've met, and so there are lots of things that we're doing together, like giving some talks or some sets of lectures, and so we had that kind of interaction as well. And in 1992 we overlapped here, because Peter, as Ulrika has just explained, was very instrumental in setting the whole place up, and he was the deputy director, and Michael Green and Raymond Lickerish and I were actually asked to run one of the first two programs at that time. So we ran a program from July to December 1992, and it was on low-dimensional topology and quantum field theory. It was a very, very nice experience in many ways, and it was a very, very active program. We had many people coming from all over the world, and one of the nice things that one of the participants said about it was, I seem to remember, Sasha Balavin, who some of you may remember and know, said that this was just like the Landau Institute used to be in its heyday. So there were people discussing at blackboards, there were people having coffee time seminars and so on, and it was just perfect. So I think he made that comment, and that's exactly how it was. And I remember we had a contingent from Japan. Quite a lot of Japanese people came, and my memory, although Peter's memory may be different, is that Toru Eguchi and his friends invited us to dinner somewhere in Cambridge. I don't remember where it was. And we went, and they looked after us very nicely. And somebody took a photograph. It wasn't Toru because he's there, but he sent me the photograph afterwards. So I'm afraid I don't know who actually took it, but it's just evidence that Peter was actually there and still smiling, even though he was deputy director, which is a very harrowing thing. Actually, one of the things that I learned from that, which was less evident in our previous interactions, is the fact that Peter is absolutely fantastic at administrative things, because he always has a very clear way of thinking about stuff, and he has a very clear plan of action, and then he makes sure that it goes that way. And it's very effective. And so it's not surprising to me that he then became master of St. John's, and then subsequently after that became the director of the Institute in Princeton, because all of these places were undoubtedly gained from his capacity to administer and manage things exceedingly effectively. I don't think he ever did a stint as head of a mathematics department, but I might be wrong about that, which is an alternative thing that many people have to do. But I'm sure he would have done it absolutely excellently had he had that opportunity. Okay, so I also have to give some apologies, because what I'm going to say is not going to be a complete set with a complete set of references. There's just no time. There won't be too much detail because two reasons. First, there's no time, and secondly, I can't remember all the details. And one of the sad things is, I'm afraid, is that the grey cells stop being very efficient after a time, and I'm afraid I've reached that time. I'm a little bit younger than Peter, but not terribly much. So I can't cover everything, and I can't remember everything. But nevertheless, let's have a go and see what sort of things that Peter was up to in the distant past. So as I've already mentioned, he was a student when Veneziano's paper came out, so I don't think he really worked on that as a student. But my memory says that I went to some lectures given by John Polkinghorne and then by David Olive, who was visiting back from CERN, because he spent a lot of time at CERN in those days. But I remember going to those lectures, and it's possible that Peter went to them as well, but I'm not absolutely certain about that. But we learnt about it that way, and then he went to CERN. Now, CERN was a hotbed of activity in exactly this area in exactly that time. There were other places around the world where there's a lot going on, but in CERN, there was a huge amount going on in a group that was surrounding Daniele Amati and Sergio Fubini. So I'll just have a little list here. He worked on one-loop amplitudes in the model of Neveu and Schwartz, which had come out in 1971, so he got onto things pretty quickly, and then worked on a sort of model that had been created by Virasoro a little bit later than the Veneziano model, and he worked with Charles Thorne and Richard Brouwer on how to really try to understand the nature of the dual resonance model, which had been reformulated in various ways, which I can't go into, but one of the problems was whether there was a real unitarity, and absence of ghosts and so on, in the dual resonance model. And that paper with Charles Thorne is actually now a rather famous paper, the so-called no-ghost theorem, which Peter worked on, and I think it was published in 1972, so quite a long time ago, 53 years. But that was very important, and of course, around that time, there was all the issue of the fact that the dual model worked best in 26 dimensions, and that there was a tachyon, and that the first excited state was a little bit like a photon, and so on. So there were lots of things in the air, and Peter was very definitely absorbed in that, immersed in that. And you can sort of detect, I think, in the later things that he took up, that all the seeds are sort of lying around in that time. So it all started with the time in CERN. But maybe Peter's memory is somewhat different to mine, but that's how I can see it. And then he moved to Durham, and as I've already mentioned, I also moved to Durham. But one of the things that happened just as Peter arrived in Durham, or shortly afterwards, he completed the very famous paper with Geoffrey Goldstone, Claudio Rebbi, and Charles Thorne. So this is basically the original string paper. Let me say just a few words about it. So the idea that the standard dual model was somehow associated with strings actually had been in the air for a bit. I mean, people suggest these things without really pinning down all the details or really formulating things in a rigorous way. So several people had made suggestions, and so it was not really that surprising. But this paper is really a beautiful paper. So starting from the Nambu-Goto action, which is just the area that the string sweeps out as it's moving through space-time, then they simply started with that and then worked out in a rather rigorous and nice way the classical dynamics of an open string. There's even a little piece of phenomenology in here. You have to read the paper carefully and then you will spot it. You have to think what a string is like. When it's an open string, the ends are moving at the speed of light, which is all by itself a little bit surprising. But it's also spinning and it's wriggling, so you've got a lot of dynamics going on. But it's kept together, so to speak, because there's a tension. So it's spinning, so it wants to sort of extend itself, but it's got a tension. And the tension shows up as being related to the slope of the Regge trajectory, which I mentioned at the beginning, and which maybe some of you know about, but I can't go into it. But the little piece of phenomenology tells you that in order to get a Regge slope of approximately 1 inverse GeV squared, which is the scale of standard hadrons like the proton and so on, then you need a tension of 13 tons, which is quite significant. But it gives you some idea of what's keeping these things together. So if you go away and read that paper, it's a recommended reading, it seems to me, for every single theoretical physicist of any kind. You just read it and see, you will find this thing. And it makes clear the role of the Virasoro algebra, which of course Peter continued to work on for many years afterwards. It sort of explained why the critical dimension is 26 from a very interesting point of view by looking at the Lorentz generators. So it has to be a relativistic string, so the Lorentz generators have to do what they do correctly. But on the other hand, you're quantizing in a gauge which is manifestly fixing the frame, so therefore you have to do a bit of work to make sure that it all works out right. And they did that. Very, very beautiful piece of work, and as I've already said, to my mind, this is really the beginning of the story. So the superstring comes about 10 years later, but this is the beginning of the business. And Peter was right there, and it came out just after he'd arrived in Durham, if I remember correctly. Now, I couldn't find a picture with all 4 authors, but I did find a picture when I looked through my collection of photos at home, which contains 3 out of the 4 authors, and one of them you recognize immediately, the other 2 most people will recognize, and then perhaps Peter can remember who took this picture, because although it's in my archive of pictures, I didn't make a note of who actually took it. So there it is. So Peter is in the middle there, and Geoffrey Goldstone is on the right. Charles Thorne is hidden slightly, and you can ignore me because I wasn't on that paper, of course. But that's 3 out of the 4, and then Geoffrey's wife is in the picture too. But I'm afraid I don't remember who took it. But maybe Peter remembers who took it because he's looking at the camera, and maybe his memory is better than mine. It's possible that it was David Olive, but can't swear to that. Anyway. So, one of the things that we worked on together, and I want to say a few words about things that we did together, if I may, just because it's good for my brain to start thinking about them again, and maybe Peter would like to think about them too. So I've already mentioned the Neveu-Schwarz model, which turned up in 1971, and this was an idea to sort of elaborate the Veneziano model to make it more suitable to actual bosons like the pion. So I won't go into that and how it works, but that's what they did. And then there was a dual fermion. So Pierre Ramon created a sort of extension of the Dirac equation, which when you look back at it is a very beautiful innovation as well, actually. Those 2 ideas turned up in 1971. I won't go into it too much, but as I've already said, the Ramon picture generalizes Dirac's picture of fermions and makes it more suitable to fit into the dual model picture. And in effect, although again I'm not going to go into it, this introduces 2 different representations of the, as it is extended, because there are now anti-commuting type operators as well, Virasoro algebra. So 2 new representations that weren't there in the beginning, but they were introduced here. And 2 sorts of vertex operators to add to the zoo of vertex operators. One that corresponded to fermion emitting the boson, and then one where the bosons coupled to themselves. So therefore, you could build amplitudes which corresponded to a fermion emitting 2 bosons, or 4 bosons interacting with each other. So you could construct these amplitudes. Again, I can't go into it, but that was all done, of course, and the properties they started to investigate. One of the things you want to investigate is whether the no-ghost theorem still works. Because you've extended the model, you have to check that it still works properly. But anyway, I won't go into that too much, but if you've got amplitudes representing those 2 processes, then you might very much like to increase the number of fermions. So you want to introduce or calculate 2 new amplitudes at least, or you could generalize to more particles. But you need to do that sort of thing. And that hadn't been done, except that David and I produced this vertex in 1972. And that vertex sort of intertwines the 2 new representations. So it converts the Neveu-Schwarz to the Ramond model, or vice versa, and intertwines the 2 Virasoro algebra representations. But it does it in quite a curious way. And Peter came back to work on how these things really work properly with one of his research students, Roger Horsley, quite some time, well, a little time later. So people got interested in this, and there were quite a few people interested in it, and Peter was one of them, and I was another one, and then David Olives was another, and Lars Brink, and Joel Shirk, and a few other people. And then we wanted to calculate this thing, and it was a bit complicated to do it. But first of all, we did manage to extend the no-ghost theorem. And then we contributed to calculating this 4-fermion amplitude. I won't go into that, except to say that it was also done by 2 other groups of people. Well, one by one person all by himself, Stanley Mandelstam, and then John Schwartz and Jincheng Wu. They did the same calculation, but they did it in a slightly different way in the case of Stanley Mandelstam. Well, actually, a significantly different way. And John Schwartz and Schwartz and Wu did more or less the same thing at more or less the same time. Now, this was not entirely straightforward. And I'm not going to say why, except to give you a sort of flavor of the thing. So you had to calculate several things that involved infinite dimensional matrices. So M and A here are infinite dimensional matrices. A is the antisymmetric part of M, and the matrices are built out of binomial coefficients, and they look like that. Now, nowadays, I imagine that everybody knows how to do this kind of thing, but in 1973 or 72, we didn't know how to do this kind of thing, I'm afraid, and therefore it took a while to do it. But in the end, we succeeded with the help of Russell Smith, who was a pure mathematician in Durham. He was an expert in ordinary differential equations. He was an analyst, but he was also interested in all manner of other things. So if you had a conversation with him at coffee time, he was always interested in knowing what you were up to. And he somehow took this on board and helped us by producing some tricks that we didn't think of. So anyway, and the other interesting part of this was how the Fiat transformation works. So you want to cross from the S channel to the T channel, you need to understand not only where all the poles go and so on, but you need to understand how the Fiat transformation works. We did that. And I remember Peter being very, very clear on exactly how that worked and explaining it to everybody else. And it was a very nice thing. And this illustrates another thing about Peter, if I dare to say, and that is the fact that once he's got a problem on board and he thinks it's an interesting problem, then he's like a dog with a bone. He's not going to give up. He keeps trying to find the way until he actually finds it, and usually he does, as his record demonstrates. This was an example of that kind of thing. And then, as I mentioned, he came back to this some time later with Roger Horsley and investigated this sort of intertwining relationship between different Virasoro algebra representations in more generality in a couple of nice papers. Now, in 1991, I didn't have any other photos of a physics sort of quality from the 1970s, but in 1991, there was a workshop, and again you can see Peter, this time with David and Charles on the front row, and I think Paul Montague, but I might be wrong. I'm right. And then behind you begin to see a few people who, some of them might very well be in the audience actually. And then when you go on to look at the whole thing, which unfortunately is a little bit small for the people at the back, then you begin to see that Peter's collaboration group is actually very large, because he's had a huge collection of students and also a huge collection of collaborators. So some people in this room are there. I think actually Ulrika's there. You spotted yourself. Very good. And there are other people on this slide that are in the room. Adrian is there on the right somewhere. I think Graham is on the back row. Louise is on the front row, and so on. So, oh yes, and Vaughan Jones is there on the right, and next to him, Adrian Oknianu. I think, yeah, Claude Ixixon is there. Jean-Louis Gervais is there. So there's plenty of people there, and Peter collaborated with many of them. This photo is freely available. I've got a copy in my filing cabinet, but I've had it since 1991 or thereabouts. But actually, if you go to the Durham London Mathematical Society Symposium website, there's a very large number of pictures going back to about 1974 when these symposia started. Unfortunately, they've now finished, so it doesn't happen now. But there you are. So Peter has a very large family of collaborators and colleagues who've worked on various things over the years. Now, time is running down, but Peter also worked on other things where duality comes in. So magnetic monopoles were investigated by several people in the past, but most significantly probably by Dirac in 1931 and then later on in 1948. And the thing that everybody remembers is that if there's a magnetic monopole somewhere, then electric charge must be quantized. And that was Dirac's idea, because after all, electric charge is quantized, so there has to be a reason for it. And that was his idea. Unfortunately, no one has yet spotted a magnetic monopole, but they exist as solitons in Yang-Mills Higgs if you've got a simple gauge group. So the standard model gauge group is not a simple one, unfortunately. It's got 3 factors, so it doesn't fall into this category. But if you've got a simple gauge group, like SU5 or E6 or something like that, then magnetic charges become a prediction because the magnetic monopoles occur as solitons. Now, this was pointed out by Tuft in 1974 and also by Polyakov in the same year. And my memory is, but again it may be faulty, that Peter, I, David Olive and many other people went to the London conference in 1974, which was in the summer. It was the big high energy physics conference, which happened to be in the UK that year. And Tuft gave a talk about his monopoles. And David Olive in particular was taken by this, and later in the same year, we again met in Aspen. And my memory is, but Peter's memory may be different, that David Olive actually gave a talk about this then. So very rapidly, he jumped onto this, and the rest is history, so to speak. So David and Peter and other people took this up and generalized things and understood things in a more systematic way over quite a few years. But anyway, it was pointed out first by Tuft and Polyakov in 1974, and most of us at that time didn't know much about magnetic monopoles from the Dirac point of view, because it wasn't something that people learnt about automatically, so to speak. And also, most people didn't know much about solitons either. Now, solitons was an activity that of course, had been going on in parallel to particle physics, but in the applied mathematics community, and famously now by Skyrm, Tony Skyrm, who followed his own path and was allied to this in some ways that most of us didn't at the time appreciate, I have to say. The first soliton talk I ever heard was actually, I believe, now again my memory could be faulty, was by Jeffrey Goldstone, because he gave a talk about sine-Gordon solitons in DAMTP when I was a student. And this was an eye-opener to me, because from time to time I'd seen the sort of Skyrm-type papers appear in the preprint rack and hadn't paid much attention. But this talk by Goldstone was a real eye-opener. And so when this came along, the idea of a soliton was not totally alien, but we didn't know too much about it. And now, of course, we know a lot more about it because everybody learns about it at school, which is good. One of Peter's famous papers is his classification of monopoles with higher gauge groups, which he did with Jean Neutz and David Olive in 1977. And then he and David wrote a beautiful review of magnetic monopoles and solitons and all sorts of things, which you can find in the library. If you haven't already got a copy, it's definitely worth looking into, because it's very informative in all sorts of ways. So, then came instantons in 1975. And again, I'm really running out of time, but Sasha Belavin, who was here in 1992, I mentioned already, is one of the inventors or discoverers of instantons. And these are solutions to the self-dual Yang-Mills equation. And of course, the original instanton had charge 1. So you compute the charge by doing this calculation of the action with a self-dual field. That's just a number for topological reasons if you're working in Euclidean 4-dimensional space. So I won't go into all of that, but one of the consequences, of course, was the prediction of the axion, which now people are currently actively looking for, because it's one of the candidates for dark matter. And people of a more mathematical bent started looking for solutions which had k bigger than 1, and they were known to depend on a large number of parameters. Now, this is a long story, so obviously I can't tell this story. The very critical first step, apart from some special cases that were worked out prior to this, was Richard Ward, who made use of Penrose's twistors to reformulate the whole question as a problem in algebraic geometry. And once it's a problem in algebraic geometry, there's a whole zoo of other methods that you can start to use. And so they did. And so Richard's work was followed by work with Atiyah in 1977. And then after that, Atiyah, Drinfeld, Hitchin, and Manin wrote their famous paper in 1978, which gave a very nice construction of the instantons, which we were able to understand. So, Peter contributed this in lots of ways. First of all, we tried to understand the Atiyah-Ward way of thinking, and we understood a little bit, I think, a little bit better the Atiyah-Ward ansatz, and we related them to Beckland transformations, which sort of swapped you from one sort of ansatz to another, and that was quite nice, and it was useful later, so we'll come back to it. And then we played around with the ADHM construction for a while, and again, I can't go into it, but it involved trying to do specific computations which would be useful for actual computations in a quantum field theory. So we looked for the Green's function for a covariant Laplacian and found this nice formula for it, this one. I won't go into this because time is running out, and found solutions to the Dirac equation in a general instanton background. Again, in terms of this quantity V, which allows you to construct the gauge potential. Now V hides a lot of secrets because it's not a square matrix or anything, it's a more complicated object. It's, so to speak, a vector whose components are matrices. And it enables you to construct a lot of things in quite an explicit and concrete way, which is possibly useful for people who really want to calculate stuff. At least that's what we thought. Chris Stanton and Weinberg did more or less the same thing at pretty much exactly the same time. So there were lots of people thinking about these things. And then the Green function results were generalized, and then he started to work on another thing, which is calculating the determinant of the covariant Laplacian, which is something else that you might want to know if you're calculating in quantum field theory. So we did that for a bit, and we made use of zeta function methods alongside Hugh Osborne, who's also here. And later on, Peter with Paul Mansfield and Hugh generalized that because the first paper didn't finish the job, but the job got more completed in the second paper with Hugh and Paul. And then we extended the ADHM construction to higher dimensional gauge theories in 1985 with Adrian. And then we came back to magnetic monopoles because magnetic monopoles had moved on slightly because in 1975, Prasad and Sommerfield found an exact solution provided you switched off the self-interaction of the Higgs field. You keep the boundary condition at infinity, spatial infinity, and you switch off the interaction of the gauge of the Higgs field with itself. So that's sort of a slightly odd thing to do, but it gives you an exact solution in terms of simple functions, you know, hyperbolic cosines and sines and tans and so on. And then Bogomolny pointed out that the equations that you were actually solving, if you did this, were looking like this. So phi is the Higgs field. This is the covariant derivative of the Higgs field, and that has to match the magnetic part of the non-abelian field, and that's how you construct a monopole. Alongside the boundary conditions on the Higgs field, that's the equation you need to solve. And the point is that Bogomolny noticed that if you think about the Higgs field as being an extra component to the gauge field, so the gauge field, you're looking for a static solution, there's no time dependence, depends only on 3 space variables. If you think instead that phi is the time component, then these are exactly the same thing as self-duality equations. And then you can go back and try to use the previous technology. And that's exactly what was happening. But before I get on to just saying a few words about it, Nick Manton noticed that if you have 2 monopoles of the same charge, you'd expect them to fly apart because you'd expect them to repel each other. But what Nick noticed was that in this limit where you switched off the Higgs self-interaction, then the interaction between the two monopoles due to the Higgs field exactly cancelled out the electrostatic or the magnetostatic repulsion. And therefore you could look for solutions that had two or even more monopoles just sitting there doing nothing because the Higgs fields exactly cancelled out the magnetostatic repulsions. That's an amazing thing when you stop to think about it. But anyway, that seems to be the way it is. And then it became possible to find multi-solutons, because multi-monopoles, because you could then use the techniques from self-dual gauge theory suitably adapted. And that's exactly what Ward did in 1980. Peter Forgas, Zalan Horvath, and Lotzi Pala in 1981 also produced a multi-monopole, but it was a special one with axial symmetry, and they used a slightly different technique to solve the self-dual equation. But then Peter and I came back to that and found a way to generalize Ward's solution. It wasn't entirely an explicit thing, but we did generalize it a bit and found a solution which had as many degrees of freedom, 4n minus 1, as it should have if the total magnetic charge is n. And then the ADHM construction of self-dual gauge fields was then adapted by Werner to solve this problem as well. So the ADHM construction was a different way of thinking about the self-dual gauge fields. But how do you construct the ADHM construction in order to adapt to monopoles? Well, we played with that for a bit with our students. So there were two students of Peter's, I think, and one of mine. And we played with this for a bit and used Werner's method to calculate spherically symmetrical monopoles. And again, these had been found before, so that we could check things. But it was more complicated. If you look back at the paper, I'm amazed that we managed to do it at all, because it's quite complicated. And then key to Naum's construction, or Werner's construction, is a set of ordinary differential equations, which I can't go into very much, except that if the monopole has charge n, and we're talking about an SO3 or SU2 gauge theory, then the matrix functions, three matrix functions, are n by n, and they satisfy these equations here with suitable boundary conditions. And the width of the domain is related to the length of the Higgs field at infinity. So that was a beautiful thing, and it turns out that those are also self-duality equations, but in a hidden way, because this time there's only one independent variable, namely z, which is like a time. And then the three space-like variables are missing. And that suggested another idea to Peter and I in 1984, and we introduced this idea of reciprocity. We didn't dare actually to call it duality, because duality had already been used in so many ways. So we called it something else, and that was a little bit of fun. And there we are. So in 2015, David Fairley and Holger Nielsen, Holger was another pioneer of dual models, as was David in Durham, Holger in Copenhagen, or in Copenhagen. And this photo was taken by Lee Fairley, and then David gave it to me quite recently. So it's quite a nice photo. And it sort of mirrors a bit the earlier one. So Peter is a very convivial person. He likes to have dinner parties. He likes to have lots of people to have conversations with, and he's always telling stories and so on. And here, he's been listening to a story from somebody else, or he's been telling a story, and we only can guess at what it was unless he wants to, or David wants to tell us what they were talking about. Okay, so I now want to just end with a huge thank you, really, to Peter first of all, for a long collaboration, which I've given you a little bit of a flavour of, on dual models, self-dual gauge theories, magnetic monopoles. For friendship, help, advice and encouragement. Well, in various times of my life, I've needed a bit of support, like everybody does. And Peter, when we've been in the same place, has always been very generous with his support. So I appreciate that very much. And also very encouraging. I also have to say that he's very patient, because he is, as I mentioned already, a very focused person. He likes to do things in a very systematic way. And anybody who's had a sight of his research notes will know how well organized and everything he is. I, on the other hand, are somewhat, I don't know what the correct terminology is, but I get easily distracted. So, I'm in the middle of a calculation and I see a paper on the archive and I suddenly go in that direction, which is very exasperating probably for other people. But Peter is very patient, and I really appreciate that over many years, actually. It's hard to think how many, but anyway, something like that. And also I'd like to thank Helen for her constant support for Peter, because Peter too has had his ups and downs over time, I'm sure, and also for welcoming us to their house on countless occasions when we've enjoyed their hospitality. So thank you very much for all of that, Peter. And also, not only that, Peter has had many successful PhD students. I mentioned that already, but they've also worked with my own PhD students or ex-PhD students. So for example, Tim Hollowood worked with Paul Mansfield on S matrices in two-dimensional quantum field theory. Neil McKay worked with Gerard Watts on some aspects of Toda quantum field theory. Peter Bocock with Patrick Dorey and Christina Zambon. With Patrick, we worked on affine Toda field theories with boundaries, quite a long time ago now, 30 years ago, and with also on this idea of quantum field theories with integrable defects. Well, obviously I don't have time to go into any of that, but I would like to, but it's not possible, so sorry. So thank you, Peter.